All right, so number 3 from chapter 7. This is the calculate the work done on an elevator car question.
Yes.
All right, so this is a good place to start.
Okay.
Um, so actually, we can go at this a couple of different ways. So
Oh,
the very first way, let's get a force analysis out of the way first. So here's our elevator car.
oh, I'm sorry. I still can't see
Oh, okay.
what you're writing on.
Um, there. Is
Oh,
that? Are
okay.
we good?
Thank you.
Okay. Cool. Cool. All right. So we have an elevator car. The cable, the tension in the cable is pulling it up, and the weight of the car is pulling it down. So if we are at constant speed, that means that the sum of forces has got to be 0, right?
Yes.
Um, which just tells us that the tension in the cable is equal to the weight. So armed with this information, we can just apply the definition of work. So
Okay.
work is provided by a force which acts over a distance. Oh, actually, hold on. There is some friction here. Friction averages 100 newtons. So minus 100. All right. So the if it's being lifted at 40 meters, lifted by 40 meters, then the amount of force that the tension is providing is the weight plus 100, and it's being lifted by 40 meters. The weight is what, 15,000, and so this whole weight here is 15,100.
Okay. And then just put that into the calculator.
Right. So this is like 600,000 or something.
Okay. Yeah. And that was for just part A? Oh no, never mind.
Yeah. So yeah, that's part A. So
Okay.
remember, we have two different perspectives on gravity, and the perspective that this question is asking for is it's asking for gravity to be treated as a force which does work. And so the this is work done by tension. So the work done by gravity might start exactly the same, except the weight is pointing downward, right? So it's 180 degrees different from the displacement, right? So if the displacement is positive, then the weight must be negative. So we have minus, and so this is approximately negative 600,000. Does that make sense?
Yes, it does. Thank you.
Okay. Hey Jasmine, yes, I am recording this for sure. Yusuf, why do we use kilojoules instead of joules? Um, Aesthetics. So, just because I I find it aesthetically pleasing to have numbers smaller than 1,000, like between 0 and 1,000. But you could definitely write 600,000 joules. That is perfectly okay.
I have a question.
Sure.
I noticed that when the people were like solving this type of questions, their equation for work was force times the displacement times like cosine of an angle. So are all of our questions that like on the exam like we don't need like the cosine of an angle, right?
That's
Because I
actually
was like,
that's a really good question. So your book does write something like force, distance, cosine theta. Um, so this is what your book writes. The way I learned it originally, and so this is what's always in the back of my head, is that only the part of the force that is parallel to the displacement counts, and that ends up being F cosine theta. So I will try to be more mindful of that and write it like your book writes it, but in the back of my mind, this is what I'm thinking. Like we first have to only separate out the part of the force that is parallel. Does that make sense?
okay, so also like will in the exam have like questions that we have to think about whether the force is parallel, and if
Yeah,
it's not, then we use like the cos of the angle.
that's right. So if we had an object, in fact, we had one on the last exam. So we had this block of ice that was being pushed this way, but it was because of an applied force that was being applied like this, right? So not all of this pushing force does work, right? Because the um, the movement is only in the x direction. So if we wanted to say, well, how much work does this pushing force P exert when you move the block of ice 10 meters, right? Then that's going to be P cosine theta, because that's the part of the force that is parallel to the displacement. Does that make sense?
Oh yeah, thank you.
Okay. All right. Good morning, Eva. Who else has a question? So I think Asuri has a lot of them. So
Yeah, I might have a lot. It's just because I'm trying to figure out, but I don't mind just doing any problem either.
okay. Well, I mean, if no one else has something that they want to work on particularly, then you get to go. You
Oh,
get to pick the next one too.
oh, okay. All right.
Someone's got a question about number 16. Why do we divide the potential energy of the generators by the energy of the fusion bomb rather than the other way around? Um, that is one of those questions that sounds completely insane out of context. Let me take a look at this one real quick. What is the gravitational potential energy relative to the generators of a lake? Compare this to the energy stored in a 9. Oh, so yeah, it doesn't matter which way you divide it. Like, because you just want to see, which one's bigger. And, yeah. So it's okay to say, the lake is 120% the energy of a fusion bomb, perfectly okay to say also that a fusion bomb is 85% the energy of the lake, whichever way you want to go about that. Do we want to work this problem out while we're here, though? Anybody? Okay, that's a couple yeses. Let's do it. So we've got a dam. So imagine this is like Lake Mead behind Hoover Dam. So in general terms, the way a dam works is by taking the gravitational potential energy of the lake that is stored behind the dam. It lets that water fall, which lets it trade the gravitational potential energy for kinetic energy, and then it uses a turbine to convert that kinetic energy into electrical energy. Okay, so the volume of this lake is 50 cubic kilometers. Is that a lot? How big is a lake? How big should lakes be? How big is Lake Mead? Okay, that's the surface area of Lake Mead. But since we're talking about volumes, we should talk about cubic kilometers of water, right? Yeah, it's about 30 cubic kilometers. So this lake is bigger than Lake Mead. So this gives us something like 2 times 10 to the 16 joules. So, anyone know offhand how much energy is in a ton of TNT? So this is what I would consider more of a conceptual problem. You definitely could draw a diagram for this. This would be something like water. .8 times 10 to the 16, that's the energy of the fusion bomb. Is 9 megatons a lot or a little for a fusion bomb? it is definitely more than the Hiroshima bomb, which they were in the tens of kilojoules, or tens of kiloton range. So this bomb that we're talking about here is literally 100 times more powerful than the Hiroshima bomb. Sadly, that is not by far the most powerful bombs we have on hand. So there are definitely 100 megaton bombs out there. Alright. So the energy stored in this lake is about half the energy of one of these mid-sized bombs. Questions or comments? A question I used to ask a lot in labs, when I taught the labs, the stated power output of Hoover Dam. Hoover Dam produces 2 gigawatts of energy, like 2 gigawatts of power on average. Right? And then ask the reverse question, how much water has to pass through Hoover Dam every second in order to give us this power output? Right, but this is just the reverse of the question that we've just asked here. All right, what should we consider next? Got a request for number 56. We've got a swimmer. This is much nicer to consider than fusion bombs. So we're told the average horizontal backward force of the stroke is 80 newtons. So obviously there's going to be more backward force at the very bottom where your movement is actually pointing backwards than there are at the front or the end of the stroke. But they're saying average, right? So they're making our lives simpler. So how much work does each stroke do? Right, so again, work is equal to a force applied over a distance. We're defining positive to be backwards. That is a good question. We might as well. Yeah, we might as well. Note that even though the swimmer is doing work in the backwards direction on the water, the reason the swimmer moves forward is because the water, equal and opposite amount of work on the swimmer, right? Calculate the power output of his arms if he does 120 strokes per minute. So we have 144 joules per stroke. Times 120 strokes per minute. Times, say 1 minute is 60 seconds. So this is about 290 watts. Questions or comments?
So when finding power, we always have to find work and then like convert that into watts using like the stoichiometry.
Yeah, so in general, power is going to be an energy per time. Right? So we could also have said something like 120 strokes per minute means that it's half a second per stroke. So we could also have said that it's 144 joules per half second. And that would give us the same answer. Was that what you were asking?
Yes, thank you.
Okay. No, the construct your own problem type questions from the book are just for your practice. So, Guy, do you mind if we check and see if anyone else has got a problem that they were hoping for, and then we will circle back to that.
Yeah, I don't mind.
Thank you. Suri, you've been patient. Did you have another one that you wanted to go over?
I was looking at number 12, but I don't know if that's like a maybe I'm just overthinking it. I don't know.
I mean, that is something that happens a lot.
And I keep just doing that with all these questions, and then just like the anxiety kicks in for this.
Okay, let's do number 12, and then we will head over to 25.
Okay, thank you.
Mhm. All right. Calculate the force needed to bring a 950 kilogram car to rest from a speed of 90 kilometers per hour in a distance of 120 meters. So this is, we could definitely solve this problem with kinematics if we wanted to, right?
Oh, so we can just start with okay,
No, no,
I
no.
understand.
Don't use kinematics, right?
Oh, don't use it?
We could, right? So this is one of the intermediate cases. Like we could solve this problem with kinematics, or we could solve it with energetics. Uh,
Okay.
what they're trying to get you to realize is that if you can, energetics is a way simpler way of doing it. So I would actually like to show both methods, and then you can see, like, actually the energy perspective simplifies this a lot.
Okay, that would definitely help. Thank you.
Okay. So the first thing I want to do is convert this 90 kilometers per hour. So, well, actually, the first thing I'm going to do is draw a picture. So we have a car. It says 950 kilograms. That's like a compact sedan, right? So it's got some speed lines. We'll call this situation A. And then later at situation B, no speed lines because it is stopped. And the distance between these two situations is 120 meters. All right. So our initial velocity is 90 kilometers per hour. It would be much more convenient if this was in meters per second, though. So we're going to do a little conversion there. So we got 1,000 meters per kilometer. And 1 hour is 3,600 seconds. So this is what? Just 25 meters per second? Okay. If we wanted to solve this using kinematics, we could look at this and say, well, we have a distance, we have an initial velocity, we have a final velocity. We could analyze this using K3, right? So we could say, all right, v squared equals v naught squared plus 2a delta x. And then we can solve for this acceleration. And our our final velocity is 0, so this becomes negative, 25 squared, 625. And then over twice the distance, so over 240. There's 2.6, where the negative sign just says that just is an indication of direction. So if to the right is the positive direction, then this means that we're going to the left. All right, if the acceleration is the net acceleration, rather, is negative 2.6, then we can bring out Newton's second law and say the force required to produce that acceleration is equal to ma. So that is going to be 950 times negative 2.6. So that's going to take a force of, we'll say 2470 newtons. All right. Any questions so far on the kinematics part?
Not yet.
Okay. If we do the energetics perspective instead, then our perspective here is that work is caused by a force applied over a distance. And I'll put the cosine theta there. And that causes a change in energy. So here we've got F delta X equals, and then the only kinds of energy we have are kinetic energy, and our final kinetic energy is 0. So we just get minus 1/2 mv0 squared. So the force is equal to minus mv0 squared over 2 delta x. So we have 950, 625, all over 240. And of course it gives us the same force, right? So the energy, so looking at it from the perspective of energy, did the same work as kinematic equation plus Newton's second law. I say work, gave us the same outcome as kinematics plus Newton's second law, but in a more compact form. And this is a relatively simple case, right? So if we were stopping on a hill, right, or if we were stopping, or if right, so if we were stopping on a hill, that would be even more problematic from the Newton's second law perspective, because now we'd have to break down, the weight of the car, the friction of the car. It's pointing up the hill, down the hill. But in the energetics perspective, we don't actually care about any of those details. We just care about initial speed, initial height, final height. Done. All right. Questions or comments on problem number 12 here? Actually, this is not A and B for the question. This is kinematics and energetics.
For part B, can we continue with the energetics method?
Oh, yes, absolutely. Let me
Okay,
make a
thank
little
you.
bit of room here. So I used a lot of colors on this page. What have I not used on this page? There we go. Blue. So for part B, it's actually the same setup as we had in green, right? So the force required to take an object from some kinetic energy to no kinetic energy is going to be minus mv naught squared over 2 delta x, except now our delta x is 2 instead of 120. So now instead of 2,400 newtons of force, we're looking at 148,000 newtons of force. So 60 times more force. Yep, that is why you die when you hit a concrete wall, but not when you hit your bricks, even though the same amount of work is done. Yeah, negative sign just indicates direction. Alright, so for our roadmap, we had a request for 25, but then we also had a request to do something from chapter 5. So let's do problem 25, and then we'll do Eva's question from chapter 5, and then we will circle back to 23. Oh, chapter 7, number 5. Okay. So 25, then 5, then 23. That's our roadmap. And then we will hit last week's group quiz question again. All right. So let's say you are driving and you stick the car in neutral right as you start to go up a hill. How far up the hill can you make it? So here's our hill. Here's our car. So in situation A, we've got some speed. In situation B, we have height, but no speed. And 110 kilometers per hour is about 30 meters a second. Alright, so our height at situation A is going to be 0. At B, our height at situation B is something, right? That's what we actually want to know. And our velocity at situation B is 0.
May I ask why velocity is 0 in this situation?
So for part A, we're looking for the highest that you could coast, right? So if velocity were still positive, it means you'd be still going up the hill. So that's not our highest point. And if velocity were negative, that would mean that you'd already started to fall back down the hill, which means we're not at our highest point. Does that make sense?
Yeah, it does.
Okay.
It's kind of like free fall, right? The max height is when for a second it's 0.
That's exactly correct. Yes. Okay, so this is for A. So in part A, we have no friction done, and we're going to use the perspective that gravity is a source of potential energy and not a force that does work. So if we use that perspective, then actually there's no work done from A to B. So the work done from A to B is 0, and that's going to be also the change in energy. So we have energy conservation from A to B. Right, so the total energy at A equals total energy at B. What kind of energy do we have at situation A?
Kinetic?
Exactly correct. So 1/2 mVA squared. And what kind of energy do we have at B? Yeah, just gravitational potential. Masses cancel. And we're going to get that the height that we can coast up that hill will be equal to VA squared over 2G. So 30 squared is 900. So 900 divided by 20. This is about 45 meters. Questions or comments?
Does that say VA squared?
Yeah. So velocity at A squared divided by 2G is our height at B.
Where did the velocity come from in the equation? Oh, from the other side. I see it. Sorry.
Oh yeah, I have a habit of when I'm solving for a variable, I like to put it on the left. That's just my sense of aesthetics. Yusuf asks, if we considered gravity as a force that does work instead, how would the problem setup look like? So if we did that, then we would still say work is equal to force times displacement, and that equals that causes a change in energy. Where here, the force that we would be interested in is the gravity, right? And be careful about our direction here. And so up is the positive y direction. So the force that we're interested in is gravity. It's acting in the negative direction, and the displacement parallel to it is what we call h. On the right-hand side, we have energy at B minus energy at A. That's what we mean by delta E. But energy at B is 0. So we just have minus 1/2 mVA squared. Negative signs and m's cancel, and we get the same results. Does that answer your question, Yusuf?
So I'm kind of confused. Like, what's the difference? I know for the first one you use kinetic and then potential energy, but then for the second one, or is this just like what are those two equations?
So that's a really good question. These are two different ways of looking at the same phenomenon, right? So if we want to think about gravity as a force that does work, that means we cannot think about it as something that causes potential energy. So if gravity is a force that does work, then there is no such thing as gravitational potential energy. And gravity is going to show up on the left-hand side of this equation, not the right-hand side. So essentially, there is no difference between one perspective or the other for almost all cases. It's just a question of whether your MGH is going to show up on the right-hand side of the equation, or you're going to have a negative MGH on the left-hand side of the equation. But, I mean, that's literally the same thing, right?
Okay, thank you.
Did that answer your question, Yusuf? Okay. Part B, what if we observed that height B is in fact only 22? In that case, there's clearly some other force at work, like friction maybe. So we have work from A to B is equal to whatever dissipative force and that's going to equal the change in energy, so which will be energy at B minus energy at A. Now for part B of this question, we don't actually want to consider how much force it is. We just want to consider how much work this force must have done. Right? So on the right-hand side, we have mg hb minus 1/2 mVA squared. And these quantities on the right-hand side are 750, 10, 22, so plugging this into a calculator, I get negative 172,500. So that's the amount of energy that whatever dissipative force must have stolen off as heat, right? Do we consider the distinction between conservative and non-conservative like the book does? Yeah, I mean, this is this is basically asking what is the work done by non-conservative forces, right? So if we have lost 172,000 joules of energy from A to B, that must mean that non-conservative forces have done negative 172,000 joules of work. Is that what you were asking? Okay.
Could we have used the equation in red to also solve for the force or no? Because it's zero.
I'm sorry, could you say that again?
Could we also have used the equation in red to solve for like part B
Oh,
or
yeah,
not?
absolutely.
Okay.
So using the red method, we could have set this up, said that the work from A to B is equal to the work done by gravity plus the work done by whatever non-conservative force, and that causes a change in energy. Right, so if we were solving for the amount of work done by the non-conservative forces, it would just be change in energy minus the work done by gravity, and then we would have exactly, that would be exactly this. Does that answer your question?
Yeah, thank you.
So yeah, whether you start from the pink or the red perspective, you'll get to the same place for sure. Part C asks us to think about what if this hill was not in fact a gently sloping hill and was in fact just a ramp. Right, and if this hill was inclined at 2.5 degrees above the horizontal, right, and raised 22 meters in the vertical direction, then how much distance along the ramp must you have gone, right? Yeah, that's right. You can use sine to find the hypotenuse. So the sine of 2.5 is equal to 22 over, we've already used h, so let's say r. D would also have been a good choice. I kind of regret choosing r now. So if we're going to be using 2.5 degrees, we make sure that our calculators are in degrees mode. And 22 divided by the sine of 2.5 gives us about 500. So from our result in blue from part B, F delta, well, I guess delta R now, or FR equals negative 172,000. So the force must be the non-conservative work over that distance. So that's like 344 newtons of frictional force on average. Questions or comments? The point allocation will look pretty similar. So you still will almost always need to draw a picture. You'll still need to specify some coordinates. So you'll need to say what's the positive y direction, positive x direction, but additionally you'll usually need to say at what height is the height 0, so that we can use gravitational potential energy. Then there'll be a point for correctly identifying the energies at like 2 different positions, and then a couple of points for solving for the thing that you're looking for. Does that answer your question, Yusuf? What do you mean the height thing still confuses you? Yeah, you choose one height to be 0 and you define all other heights in reference to that point. It's the same thing that we did for kinematics, right? If you're throwing a ball off a cliff, you have to decide whether y equals 0 is at the top of the cliff where you threw it, or at the bottom of the cliff where it lands. And as long as you choose one of those and you stick with it, then everything else works out. So to more fully answer your question, Yusuf, here's how I would have scored this particular problem. All right, a point for the picture, a point for the identifying the relative quantities, a point for writing down the work energy theorem correctly for this situation, and then a point for each of the quantities you were asked to find.
For part C, I'm kind of confused about that equation that you chose. Like, where did that equation come from? Like, is that always going to be the equation for like frictional forces?
No. It came from our result from part B. Right, so part B, like we had to use our result from part B in order to get an answer for part C. Does that?
So, like, we just like gotta divide like that side by R to get to have like isolate the F. Is that what you're doing?
Yeah. So for part B, we calculated, an F times R is actually got to be equal to this quantity. So if we want the force and not the amount of energy, we just have to divide by R. Yep.
Oh, okay. Oh, because R is distance. Okay.
Yeah.
I was just kind of confused what R was for a
Gotcha.
second. Okay.
Yeah.
Thank you.
You're welcome. Okay, anything else on this problem before we go on to number 5?
May I ask a question that's conceptual? So it's going to help us with number 5 because I did that one.
For sure.
It's just a general one about the work equation, which is FD cosine theta.
Yes.
And that angle is confusing me because it's always 0 or 180 or something like that. But when an equation gives us an angle, that's not the same angle we use in the formula. But instead, we have to break down the vector. And we'll see it, I think, in this exact problem.
Mm-hmm.
But I want to understand that cosine theta, what does it refer to in the work equation?
So that is a really, really excellent question. So when we have, right, so f d cosine theta, if we draw in a distance and a force, theta is the angle between the distance vector and the force vector. Which may or may not be the same as the angle that this ramp is pointed at, but right? Does that make sense? If it's parallel, yeah. So if it's parallel, the angle between them is 0. Cosine of 0 is 1. And if they are pointed in opposite directions, right? Then that gives us a negative work because right, cosine of 180 is a negative 1. And if they're perpendicular, right? If the force is like directly in the y direction, and the distance is directly in the x direction, right? They're 90 degrees apart. Cosine of 90 is 0.
But we have to break down that vector because it has both x and y components. And then the theta would go back to being 90 or 180, right?
Yeah, so that is one way of thinking about it, and that's actually what's usually going on in the back of my head is whatever force we have, I break it up into parts that are parallel to the distance, and those do work, and then a part that is so we might have the parallel part of this force that does work and the perpendicular part of this force that does no work. Does that answer your question?
Yeah, it does. Thank you.
You're welcome. Thank you for asking such a good question. In a couple of chapters, we will actually learn that this perpendicular part of the force isn't useless, but instead of going into doing work, it's going to tend to cause the object to spin, right? So the parallel part of the force will tend to cause movement or an acceleration, and the perpendicular part of the force will tend to cause a rotation. But that's just a preview of what we're going to be seeing in a couple chapters. That's after momentum, so it's more like chapter 10. Okay, so for this problem, we got a person pushing a crate up a ramp. The ramp is 20 degrees to the horizontal. And he pushes with 500 newtons worth of force. It's a fair amount of force. The box moves up the ramp at a constant speed. All right, whoops. Acceleration is 0. Okay. And so we have this is really a box on a ramp problem. Let's use our tilted coordinate system. So x direction is up the ramp, y direction is perpendicular to the ramp. And we've got normal force no friction. Okay. So the question says, be certain to include the work he does on the crate and on his own body in order to get up the ramp. So this M, let's view this M as the mass of the crate and the mass of the person. How do we know it's no friction? You're right, we don't. Okay, let's break down our forces. So our normal force is only in the y direction. Our friction is only in the negative x direction. Our pushing force is only in the x direction. And the weight is partially in the x direction and partially in the y direction. Okay, so if we're going to include friction, we actually have to be a little more careful here. We'll analyze just the crate first. Okay. Everyone with me on this force breakdown, though? Right? This is what we've been doing for a few weeks now. Okay. So we're told that there's a constant speed. So the sum of forces in the y direction has got to be 0. And those forces are n minus mg cosine theta, which means that n has got to be equal to mg cosine theta. And we can just get a number for that. Well, actually, we can't. We don't know the mass of the crate, do we? In the x direction, sum is also 0. And that's going to be 500 minus mu n minus mg sine theta. So in other words, 500 equals, and here I'm going to substitute in for n, mu mg cosine So we've got some unknowns here. We don't know mu, we don't know m, right? And this really illustrates the power of the energetics perspective over the power of the kinematics plus forces perspective that we had before this, right? Because we don't actually have enough information to determine even whether there is friction in this situation. All right, so we have we were able to write down 2 equations with forces, but we had 3 unknowns. We didn't know n, we didn't know mu, and we didn't know m. Right? So that becomes problematic. However, we could instead write down an energetics perspective. So from an energetics perspective, the work done on the crate is equal to the force applied times the displacement. And I'll write down cosine theta, except as usual, cosine theta here is going to be 1. And this work causes a change in energy. So the change in energy that the box experiences is going to be equal to the force that was applied to it times the distance it moved through. And we know both of those things. Right? This is 2000. Right? So that is actually that's the work done on the crate. And actually this gives us some good information, because what kind of energy was given to the crate as it was pushed up the hill? No kinetic, right? Because the speed is constant, right? So the kinetic energy of this box isn't changing. But we are pushing it up a hill, so it's gaining height, which means it's gaining potential energy. So this actually gives us enough information to solve for what the mass of the box must have been. Right. So Yusuf, there is kinetic energy both at the top and the bottom of the hill. So we might write more precisely that the change in energy, right, from the bottom to the top is the kinetic energy at the top plus the gravitational potential energy at the top minus the kinetic energy at the bottom. And these two are the same, so they cancel. So actually, the information they've given us, that's enough to say that the mass of the box is actually 146 kilograms. Because the force sine 20 is how much height you gained as you went 4 meters up the ramp. But anyway, that's actually more than what the question is asking for. They want to know the total work done. So the guy did 2,000 joules of work pushing the box. So this is the work on the crate. Then we have to compute the amount of work that the person did on themselves. So the work on the person is going to be equal to a force applied over a distance, which will cause a change in energy. where here, since we were already given the mass of the person, it's easiest to just compute their change in energy. So mass of the person, gravity, h. Right, so this is a total of, rounding here, is 1,200. So the total amount of work is the sum of these two, so it's about 3,200. Did I say? Why did I write newtons? This is joules. Why do we consider using height for the displacement value for the work on the person? We didn't, actually. So on the person, we just dropped this middle part, right? Because we're not interested in the force on the person or the displacement. We're actually just weren't interested in the amount of work. So instead, we dropped this middle part and just went for WP equals change in energy.
Is the MGH, is that like the equation for potential energy?
Yes, that is gravitational potential energy.
So like the changing energy is just gonna be potential energy. There's like, I thought it was gonna be like some kinetic energy because he's like moving up.
He is moving, but he's moving at the same speed he started with. Right? So yes, he has the kinetic energy at the top of the ramp and the bottom of the ramp, but it's the same amount of kinetic energy. So the change is actually zero. The change in kinetic energy is zero, right?
He's also like getting more potential energy because he's going up. So like, okay.
Yes, and that is what we ended up calculating here. Yusuf brings up a good point, which is that this is before the concept of gravitational potential energy was introduced in the book. So we could also easily have said the work done on the person is equal to F delta x minus mgh, considering that gravity is a thing that does work, and that because there's no change in kinetic energy, these two things are equal. Yeah, so in this dark blue perspective here, the F here is the force that the person is exerting on their own body to move themselves up the ramp, and mg is the force that gravity is, pulling down on them with. So mgh is the amount of negative work that gravity does on the person as they move up the ramp, and F delta x is the amount of positive work that the person does on themselves. And because there's no change in kinetic energy, these two must be equal. Does that answer your question? Okay, excellent.
I have a quick question. How do we figure out like the changing energy? Like I was thinking like it would be like the change in kinetic to potential, potential to kinetic. But like on the weight of the, I mean the work of the crate, like it was like kinetic and then potential then kinetic again.
For this particular crate, it always had kinetic energy, but the amount of kinetic energy it had never changed. So when we go to consider the change in energy, right, that's going to be the energy it has at the top minus the energy it has at the bottom. We're going to have we can have a kinetic energy term in both cases, like down here, bottom right. But because the initial kinetic energy is the same as the final kinetic energy, they're going to subtract off.
Also at the top, it also had kinetic and potential. It had both of them.
Yes. But it had the same amount of kinetic energy.
Would it like only have potential because it's not moving anymore on the top?
Oh, it's still moving at the top,
Oh, okay, okay.
right? But so at its basic form, the work energy theorem doesn't necessarily tell you how much energy an object has. It tells you what the change in energy is. So if a particular kind of energy is not changing, right, then that's going to fall out of our analysis.
Okay, because it's not changing because it's like constant of speed, so that means like the kinetic energy is like constant.
Right,
So it's
the
not
kinetic
changing.
energy is constant. Right.
Okay.
So like we could, if we wanted, I don't recommend this, but you could define zero height to be sea level for all problems, right? Which means that if you did a problem here in Las Vegas, all of your people would be at a height of like 700 meters. But since their height isn't changing, it isn't actually meaningful. Does that make sense?
Okay, thank you.
All right, so we had a request for problem 23. And then after that, we will talk about the group quiz from last week. Okay. I need a second monitor so bad. All right. So we have a pogo stick. Pogo stick is basically just a step on a spring, right? And the force constant of the spring inside this pogo stick is 2.5 times 10 to the 4, so that's our K. And the maximum that that this pogo stick allows the spring to be compressed is 12 centimeters. Yusuf says, I wanted to know to specifically do the step-by-step procedures in the problem-solving strategies if it was important. I'm not sure I understand what you're referring to. Let me take a look at your link real quick. Yeah, this is basically the the steps that I've been preaching all semester, right? Sketch the situation, show where the information you're given corresponds to the picture, right? Break down all the forces, see what kinds of energy you're going to have at different points, and then, right? They say, see if you can use conservation of energy. I think that's a little messy. Just write down the work energy theorem. I'll be more explicit in this problem here. All right, so we have two situations that we are concerned with here. So the first, we have a compressed pogo stick. Wow, I definitely cannot draw a person on a pogo stick when all I can do is stick figures. This is going to be hard. Okay. All right, that's what a pogo stick looks like. And at this situation, we'll call this situation A. The height is 0. The compression in the spring is at its maximum. The velocity is 0. We might consider an intermediate bit where the spring has uncompressed, but it's still in contact with the ground. How do you know when to draw after images for these? For energy and for momentum in the next chapter, we are always going to do before and afters. Because energy and momentum are ways of connecting two different situations. So here at B, our height is just the height of it's just high enough to let the spring decompress. Oh, whoops. The spring is uncompressed at this situation, and the velocity is something. And then we have a last situation. Where the child is now airborne. And since this is the top of their jump, their velocity is, again, briefly 0. Okay. All of this is step, right? So this is step 1 and 2 from what the book says. Add one more thing. We're going to say that up is the positive direction. And with that, you've done steps 1, 2, and 3 from the right, this is what I would consider steps 1, 2, and 3. Right? We've drawn a picture. we've specified coordinates, and we've done a vector slash other quantity breakdown. For the height at B, shouldn't it be minus 0.12? So, again, so this is a matter of definition. So I guess I've defined this position here to be height 0. Right? It's not the only way to define this problem. So by defining the height at A to be 0, right, that means that at B, the person is actually higher up than they are at A, so their height has to be positive. It is also perfectly acceptable to have written, wait a minute, actually, let's say that this height is 0, and then this height is negative 0.12. Either of those definitions is perfectly fine. You just got to stick one. You got to pick one and run with it. Does that answer your question, Jolyn?
Yeah, it does. So actually, that was my other question. When you fix the height for situation A, so situation A, he's pressing down, and then B, he's starting to go up, and then C, he's all the way up. Is that
Yes.
what's happening? Okay.
Yes. So,
Thank
yeah. So A is like the bottom of the compression, so the bottom of the bounce. B is when he's just about to leave the ground and get airborne, and then C is total airborne, max height.
What's the difference between H and delta X for this problem?
So for this problem, delta X is for the spring energy. Our H will be referring to the height in the gravitational potential energy. And then, of course,
But
V.
they're both like distance values in a way.
Yes, so the delta X is how much you've compressed or stretched the spring from its equilibrium length.
And then, what sort of prompted you to do 3 after images instead of 2 after images? Was it more of like an intuition thing, or I don't know?
Yeah. So to answer what this question is actually asking, you only have to do A and C. I did B.
Having a B make it easier, or
No, I just decided I also wanted the velocity at launch.
okay,
Does that make sense?
because there's no velocity at A or C. That
Right.
makes sense.
And I also
Okay.
wanted to know how fast you'd be going, like your maximum speed. So it's not in the question. It's just my own curiosity prompted me to add that in.
Thank you.
Welcome. And yeah, H is the height of the person above the ground. So, or the person's feet, more specifically, I guess. The bottom of the person's feet are a height H above the ground. Okay. Now that we've got all this, we can pull out our physics. And since this is a chapter on energy, our physics is almost certainly going to be the work energy theorem. So let's, and the work energy theorem, remember, the whole point of it is to connect two situations. So we can choose to use it to connect A and B or to connect A and C. Let's start by connecting A and C. So the work done from A to C is 0, right? No external forces, no friction, no wind drag, nothing going on here. So if there's no work done from A to C, that means there's no energy change from A to C. So the energy at A is equal to the energy at C. So what kind of energy do we have at A? Yeah, just spring potential energy. So at A, we only have 1/2 K delta XA squared. And what kind of energy do we have at C? Yeah, we have only gravitational potential energy. So we're looking for HC here. That's what the question is actually asking for. So HC is going to be equal to K delta XA squared over 2mg. That's, after all that work, that's actually not that exciting a jump. You should take this pogo stick back to the store and get a bigger one.
So, now I kind of understand, because like when I was like looking at a solution, I was just like, why were they only considering potential energies for this problem? So that's because we're only comparing A and C where there's no velocity, correct?
Right. So we very
if we were to
carefully
do-
chose two
okay.
situations with no velocity.
But if it was A and C or A and B, we would have a kinetic energy formula on the other side.
We sure
Or
would. In fact, that's
okay.
what we're going to do right now. So the work from A to B also going to be 0. Which tells us that the energy at A is equal to the energy at B. Energy at A is the same as it was above, so 1/2 K delta X squared. And the energy at B, we actually have two different kinds of energy because we've come up off the ground a little bit. So we have mgHb. And we also have some velocity. Jillian asks, why is the work 0? Just because there's no external forces working on this situation, right? So if we consider the spring, the pogo stick, the person to all be the same, to all be the system, then the only kinds of forces that we have are internal forces, right? So there's so if we had some other non-conservative force at work, it would be not 0. What about gravity? Yeah, so in this situation, I just kind of implicitly took the perspective that gravity was a thing that causes potential energy. So I'm not thinking about it as a force, I'm thinking about it as a source of potential energy. You're welcome. So the situation at B is a little messier, but it's still something that we can do. So the velocity at B is going to be, so we have 1/2 k delta xa squared minus mghb all over 1/2 m, and then we're going to take the square root of that. So I get something like, well, everything in this bracket, the bracket looks messy, but we actually have a number for everything in this bracket, so we can just plug and chug. So this is 2.6 meters per second. That's not, I mean, it's not super fast, right? That is like that is a jogging speed. So yeah, this pogo stick, not super exciting.
Wait, would we even like consider A to B for this problem specifically? Because like it's not even looking at maximum height.
Yeah,
This
no,
is just finding. Okay.
for
This
this
is just our
problem, you didn't have to consider A to B
curiosity.
at all. It's just, yeah, I just wanted to know.
And also, just because, just kind of like looking back at the problem solving steps, like the final one is just like check to see if your answer is reasonable or something like that.
Yeah.
I know for like stuff like height and speed, we kind of already have like sort of a familiarity with stuff like that.
Yeah.
But for things like energy, I don't know, I just think it's like a lot more weird to think about it from like a common sense perspective.
You are correct. So we don't necessarily have good intuitions for how much energy a thing should have. Yeah, no, you're absolutely right. It's more complicated because we don't have good intuition about that.
So like let's say we're taking the exam, right, and we want to like double check our work and calculations. How would you recommend going about it? Would you like look up average values for something online or like and see if it kind of compares to your answer? How would you go about checking that?
Uh, that is a really good question. I would say look at your powers of 10, right? So let's draw a logarithmic scale here. So here's our scale, and down at the bottom of the scale is, say, 10 to the 0 joules. So just 1 joule. This is the energy here. So 1 joule is taking something that weighs 1 kilogram and raising it by 1 meter in under Earth's gravity. So this is like picking up a book. Way at the top, 10 to the 16 joules. This is like nuclear weapons.
Fun.
Yeah. And then something in the middle, say 10 to the 6 joules. That is light bulb on for 24 hours. Right.
Actually, that kind of brings up a question. So, like, if you just turn on a light bulb, what is moving if we're looking at the unit of kilograms per meter?
Nothing is moving. It's all electrical energy, which is something that you will cover in 152.
Okay, so I don't know, I'm just having trouble like look. So are we looking if there's like nothing for the value of meters, how can it be so high then?
I guess I don't understand the question.
So if joules are kilograms per, if I'm getting this correct, the unit for joules was kilograms per,
Kilogram
uh,
meters per second squared.
yeah, meters per second squared. If there's no value for meters,
So a joule is also a volt times an amp times a second.
but we don't know that yet.
You don't.
Okay.
So Jolene, you are correct. Some of these problems, chapter 7 problems are more involved. You are not wrong. So when it comes to the exam, in fact, hold on a second. I'm pulling up the syllabus.
Wow, it's next week. That's crazy.
Yeah, but we are also behind. So, what I'm actually thinking is that we are going to we're going to cover chapter 8 this coming week. Then we are going to cover 9 and 10 on the 8th, and then we'll take the exam on the 15th.
Yay, my birthday. It's actually my birthday, and I was hoping you don't push it. What a beautiful birthday present. A physics exam.
Hey, you brought up the date, so
I know.
You know, your words are serious, but your tone is sarcastic. I don't understand. Isn't that what everyone would want for their birthday?
Absolutely.
Okay.
It's so much fun.
So, yeah, I was going to talk about that on Friday, but that's probably what we'll end up doing is we'll push the exam to the first half of our class on the 15th rather than our second half of the class on the 8th. If everyone's okay with that. And then what I'll end up doing, since it's like 7, 8, 9, 10 will be on the exam. So our first exam covered 5 chapters, and it was like 10 problems, choose 6. I think for the second exam, since it covers 4 chapters, it'll be 8 problems, choose 5. Does that sound okay? Does that ameliorate your worry, Jolyn?
A little bit, yeah, and it's still the same duration, right?
Yeah, same duration, 1 fewer problem, and instead of being 6 points a problem, it'll be 7 points a problem. So the whole exam will be worth the same, and that'll give me more room to do partial credit. All right, so we're coming up at the end of our time. I feel like there was one other question that got asked and we haven't gotten to it yet.
It was my question just quickly about the springs that our quiz last week.
Oh yeah. That's right.
I'm just confused why the first one doesn't have kinetic energy if we're pulling it down. So it went from max potential energy to having kinetic energy because we're pulling it down. But I think what's confusing too is the string. I think that's the part I didn't understand.
Okay, so we have a spring and a mass. So situation A. This is at the bottom, like the maximum it gets stretched by. And then we have something in the middle. And then we have in the middle, this is where the velocity is maxed. And then at the top, we have something where the height is maxed. Right, so it's like, and the velocity is going to be 0 at A and C because these are the points where it turns around. So it's briefly 0 at the very top and the very bottom because it's getting ready to go back in the other direction. And then I lost my train of thought briefly. What was this saying? Oh yeah, so is it the same kind of diagram that we just did for the pogo stick kid? We have to define a situation where the height is 0. And there's more than one way to skin a cat. I think that your lab, when you do it, is going to define the very top up here to be 0 height. That way the I think this is the way that the lab does it. I'm trying to speak in terms of the lab's language. And then there's also oh no. Okay. I remember how the lab sets it up. They're clever with the setup so that the 0 height is defined at the height the spring would have hung down on its own if there were no mass on it. Right? So if you just hang the spring with no mass on it, the spring would like to be this length at the orange line. And that way, when we go to define our height is just the negative of the stretch. Right, so this length here is the amount that you've stretched it by, or that it's stretched by relative to its own preferred length. Does that kind of answer your question, Jolyn, or did you want to go through this a bit more?
I think I understand it, but for A, the only thing that confuses me is that why does it not have kinetic energy? Because it's stationary?
because it's briefly stationary. Yep.
Got it. And then the middle one does have it. Because it's going up. It's
Yes.
bouncing back up. And the third one, it should be 0.
Briefly stationary before it turns around and starts falling again.
Got it. And then where would be the initial position?
So in the lab, yeah, you hook on the mass and then you drag it down here and then you let it go and it just kind of boings up and down.
Got you. Thank you.
Same setup for spring problems in general. I don't think we can generalize that. There's just too many things we could ask about springs.
And springs have potential energy, not kinetic.
Right. So there is an energy associated with how much you are stretching or squishing a spring.
And that constant that we used a few problems ago, that's for springs or
Yes, that is
it
correct.
was?
Yep.
Thank you.
But of course, since we did briefly cover the section on elasticity, essentially everything can behave like a spring if you're squishing it or stretching it. It's just the springs are the most direct way of studying that behavior.
Got it. Thank you so much for your time.
You're welcome. I will see you all on Friday.